Hello, my name is Jacob Hurst, and I am from West Texas A&M University, and today I will be discussing positron emission tomography. A brief introduction to positron emission tomography. Positron emission tomography, PET, is primarily used in the medical imaging field. It is a test utilized to view the biochemical and metabolic functions of your inner tissues and organs. The PET scan uses radioactive tracer substances that emit positrons. PET scans are most commonly used to detect cancer, heart disease, and brain disorders. Looking into a brief history of how the modern PET scan was developed. In 1973, Mike Phelps and Ed Hoffman of Washington University traveled to Oak Ridge, Tennessee to receive assistance from researchers James Kelly Milon, Charles W. Williams, Terry D. Douglas, and Ronald Nutt of EG&G Ortec. The team then started discussing the development of a new device that they named the PET-2. On the right, we can see a picture of Michael E. Phelps, one of the main engineers in this device. PET-2. In Oak Ridge, Phelps and Hoffman showed off their design of the 24 NAI-TL detectors that were fashioned in a hexagonal array. This device took into the account of the coincidence detection, attenuation correction, and image reconstruction by utilizing a proper filtered back projection algorithm. PET stood for positron emission transaxial tomography, later changed to PET instead of PETT since they removed the transaxial part of this device. On the right, we can see PET-2 and look at a brief model into what their idea was. As we continue with the history of the PET machines, we can see that PET-2 led to the production of two more subsequent machines, PET-2.5 and PET-3. PET-2 and PET-2.5 were both used to understand the math and physics needed to understand the positron emission tomography. PET-2, we can see to the right, is more for the computer side and trying to learn how they can monitor and reconstruct the images in a more effective way. As we keep going through the history, we find PET-3. PET-3 was developed in 1974 and had the first ever human testing conducted on it. The PET-3 machine used 48 of the NAI-TL detector crystals, which was only two more than that of the previous model in PET-2. This model featured a hexagonal array and a gantry that could rotate up to 60 degrees, allowing for much better imaging to be taken already over that of the PET-2 and 2.5. It was also the first model to use a computer for the controlling of the motion detectors for the gamma rays, the gantry, the bed, and it could produce image reconstruction and display all on the computer attached to it. This essentially meant that they started the process of automizing everything needed for a PET scanner. Now we want to switch to our modern day PET scanners from around 1990 up to the present. So modern PET scanners rely specifically on gamma radiation detectors and positron detectors. These PET scanners can be rotated and controlled fully by a computer that can help map the person in 3 dimensions. This is new compared to that of the previous PET models, and I think is still a developing field as we speak. So, The 3D images that they produce are then able to be saved and reviewed by doctors at higher resolutions than that of earlier models of the machine. As time continues forward, we find that there are constantly higher resolutions being developed for these scanners, where the goal is to eventually be able to pinpoint exactly where individual issues in the body are at high resolutions and possibly even be able to easily see the physical structures rather than that of just, like blobs or something like that. As we move on, we see the PET scanner purposes. PET scanners are particularly useful in the use of conducting brain scans, animal scans, and breast scans. These areas of expertise are often more used than that of others due to the price that it costs to conduct the scans. It also costs a lot more to be able to scan the whole body, just since the area that the PET scanner has to take up has to be much larger and the amount of crystals inside of it have to be much larger. So the brain scans are typically used to draw three-dimensional maps of the brain and are useful in seeing how individual parts of the brain are functioning. We can use this to then be able to see areas of the brain that cause things like epilepsy and see exactly what specific regions of the brain function and are doing abnormal activities to cause this. We can also use PET scans for breast scans so they can detect abnormalities in the chest such as tumors or anything like that that is tissue related. On the right, we can see a PET scan of a man who has a tumor present in his left lung. As I was talking about earlier, this is from I think around the late 90s to early 2000s, and you can see that the image is not very high resolution, but you can see that there is an obvious abnormality in the lumps inside of his chest. Now I will talk about the radioactive tracers that are present inside of PET scans. So the radionucleotides that decay by positron emission that are used in positron emission test tomography imaging are listed below. You can see we have carbon 11, nitrogen 13, oxygen 15, fluorine 18, sodium 22, copper 62, copper 64, gallium 68, bromine 76, rubidium 82, and iodine 124. I then have also listed the half-lives, the energy maxes in mega electron volts, and the beta plus branching fraction. And feel free to pause and read those if you are interested. I will continue now with the radioactive tracers used in PET scans, and we'll talk briefly about some of the most common ones. The most common radioactive tracers that are used in PET scans are 11 carbon, 13 nitrogen, 15 oxygen, and 18 fluorine. All of these tracers are known isotopes that emit gamma radiation once they are injected into the body. The gamma decay then releases a positron, resulting in the PET scanner being able to detect the release of it. The type of tracer that is used, I found, is highly dependent on what specific issues the doctor is trying to look for inside of the body. All of the listed tracers pass through the body with very few repercussions. I will now discuss some of the mechanics behind PET scanners. The mechanics behind PET scanners work by inserting a person into a machine that follows the shape of a hollow cylinder. The cylinder is then filled with gamma ray detectors. When the proton-rich element decays, it emits a positron, and it causes the isotope to change one of its protons into a neutron and a neutrino. We know that when a positron and an electron meet, that there is a chance that they both annihilate due to modern physics. This annihilation then sends out two gamma rays, which have an energy of 511 kiloelectron volts. Conservation of momentum then states that the two gamma rays must travel in opposite directions, which is where we coin the term coincidence detection. Crystals used in PET scanners. PET scanners use scintillation crystals that are connected to photomultiplier tubes in order to detect gamma radiation. These scintillation crystals that are most commonly used in PET scanners in the modern day are the bismuth germanate oxide crystals. These crystals are superior to the old crystals that I had mentioned back in the PET-2 scanner, PET 2.5, and PET-3 scanner. To just go back a little bit more and talk just briefly more over it, essentially why we are using these new bismuth germanate oxide crystals is because they can hold more energy and they will also result in us getting better imaging for the body. So we basically just switched crystals over so we could have better imaging. Alright, we'll now go over the image reconstruction in the PET scans. To compile images of scanned sections of the body, the gamma ray detectors have to collect a series of lines and responses, and then profile the counts versus the distance that is produced for each scattering angle. The easiest way the imaging data can be compiled or recompiled is by using a method called back projection. Back projection is found by first using an approximation of the source distribution by projecting the data from the scan profiles back across the image grid. The back projection is then also used to calculate the linear superposition of the back projections, which is essentially blurring the images before they go through the last step where they do all the filtering on the scans right before they are finally recompiled. We'll now go over some of the advantages and disadvantages of PET scans. Advantages. They are good for monitoring the functions of the brain and other organs. They can be used to find the growing rates of cancerous cells, since cancerous cells consume more sugars than that of normal cells. They are also really good for developing three-dimensional models of the human body. Some of the disadvantages to PET scans is that the patients have to inject themselves with radioactive isotopes and experience a slight gamma irradiation. It is nothing like strong enough to hurt them, but it just limits the amount that you can get per year. We also have discussed that PET scans have a high cost to produce, and which also results in them having a really high cost to use. Alright, so now I will just go over a summary of everything that we talked about, and yeah, that'll be about it. So today we discussed the history of the PET scanner and its early models and how they can differ from modern models used in hospitals today. Next, we discussed the purpose and usages that PET scanners have in modern medicine. Then we went over the radio tracers and how they work and are injected into the patient. Afterwards, we looked into the basic mechanics of how a PET scanner functions and how the physical machine is made, and what components it uses. Finally, we briefly found what some of the advantages and disadvantages of using a PET scanner are. Here's just my citations in case anybody is interested, and thank you guys for listening, and have a great day.